Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to show you how to calculate the cell potential under non-standard conditions. So I'm going to go over a couple of practice problems. In this video I'm going to go over the first one. In the next video I'm going to go over the second one. So in this problem we're asked to determine the cell potential for an electrochemical cell based on the following two half reactions. So the half reactions they gave us are these two right here. So, in order to answer this question, we need to figure out the standard cell potential under normal conditions. And so, to do that, what we need to do is take the half reactions here and fix them so that the electrons are equal. So, here we got two electrons given off, but then here we have three electrons being taken up. So, we need to fix that in order to make sure we can add those the half reactions together to a full equation. So if it goes back to when we were balancing redox reactions, one of the steps we had to do and to ensure the half reaction method would work is that before we put the half reactions back together, we would make sure that the electrons are equal for both the oxidation half reaction and the reduction half reaction. So that way, when we added those two reactions together, we would cancel out the electrons. So here we have copper. So I'm going to rewrite copper to give us the right amount of electrons. So in order to get these to the same, we would have to multiply each of these by a factor that would give us the result. So for example, 6. So if we could multiply this by 3, we would get 6. If we multiply this by 2, we would get 6. So for the oxidation, I'll rewrite it here. So for the oxidation, we would need to multiply everything by 3. So this would have to be multiplied by 3. So 3 times Cu. So that's going to be a 3 there. And that's going to give off Cu2 plus. And that's going to be a 3 as well. Cu2 plus. And I'm gonna ignore these concentrations for now, but they're there for us to use later. So then I have this here. This is going to be aqueous. And then we have 2 times 3 is 6. We have 6 electrons given off. And then for the reduction, same thing. So for this one, we're going to multiply this whole equation by 2. Oops. Maybe I'll write it on this side. So we're going to multiply this by 2. 2 times this equation. So we're going to end up with 2 MnO4 minus. And again, that's aqueous. Ignoring the molarities for now. We'll come back to that in a bit. And then multiply this by 2. So that's going to give us 8 H plus aqueous plus 2 times 3. That's going to give 6 electrons. And then that's going to give rise to 2 of those. So we'll have 2 MnO2 solid plus 2 times 2 is 4 water. Okay, so there's our now it's balanced in terms of electrons. So what we're going to do is we're going to now add these together to give us our overall redox reaction. So the 6 electrons on the reactant side here will cancel out the 6 electrons on the product side here. So that'll cancel out. Add these together and we get 3 Cu solid copper plus 2 MnO4 minus the permanganate ion, and that's aqueous, plus 8H plus aqueous, and then that's going to go to 3 Cu2 plus aqueous plus 2 MnO2 solid plus 4 H2O liquid. So now we have our full equation. So now we can put this together and get the electrode potential of the cell, the potential of the cell. So we're going to use our tabulated electrode potentials to figure out the cell potential of this reaction here. So if we look on the table for the reduction half reactions and their electrode potentials, their standard electrode potentials, we find that copper, this has a 0.34 volts. So the electrode potential here, standard electrode potential here is going to be 0.34 volts. And then for this reaction, we looked that up on our table and we find that it has a 1.68 volts. So the standard electrode potential is, what did I say, 1.68 volts. So I know the volts, the electrode potential for each of the half reactions. So this here comes from the table and is in its reductive form. And this one also is in its reductive form as well. So, but we're doing an oxidation here. And so what we would do is normally we would take that number and just put a negative there because we flipped it to get the oxidation, right? So remember that table you have is reduction half reactions, and so the electrode potentials are for reduction. But if one of your half reactions is oxidation, then you've got to flip that reduction reaction, and in doing so, you would change the sign from positive to negative, then add these together, right? So I would add, so the cell potential for this would be, the standard cell potential would be the negative, or I should say 1.68, so 1.68, and then we're going to add the negative, right, which is the same as subtracting 0.34. So we're adding the negative with the positive, and we add these together, meaning we're going to add the negative with the positive, or another way to put it is we're subtracting this number from this number. And so what we end up getting is 1.34 volts, right? So that's because we flipped this one. We got the negative, and that's where that comes from. So, but we also have this equation here, which is basically what I did here with the flipping of the oxidation here. I made this negative, it was positive. So in your table, it would be positive. So in this equation here, you're using the given reduction half reaction electrode potentials. You're not changing signs. you're going to just stick them in here because the change in the sign comes from the negative sign right there, right? But you can easily just do this equation just by thinking about what's going on here. If you have a half reaction that is oxidation, on the table it's going to be reduction, so you got to flip it. And anytime you flip the reaction in the opposite direction or in a reverse direction, you've got to change the sign of the given electrode potential that is on the table, because again, electrode potentials on the table are for reduction half reactions, not oxidation. So that's where that negative sign comes in. So another way, so if I keep this the same, if I don't change the sign and I use this equation here, then I just do E cell the electrode potential at the cathode, that's reduction. So here we have reduction, that happens at the cathode. So if you don't remember that, just remember a red cat and an ox. A red cat and an ox. So reduction happens at the cathode, and oxidation happens at the anode. Red cat and ox. Okay, so that's a good mnemonic device to help you remember where is oxidation and reduction happening in your electrochemical cell. So reduction happens at the cathode. So here I have cathode, so it's going to be this electrode potential first. So 1.68 volts. These are volts. And I'm going to subtract the electrode potential at the anode, which is oxidation. So that would be this one. So I'm going to subtract that one, 0.3. It's a positive 0.34 volts. And voila, I get the same thing. I get the same thing here and here. So it ends up being the same calculation. Okay, so this is the standard electrode potential of this reaction here. So now, once I've got the standard electrode potential, I can now use this equation here called the Nernst equation to find the electrode potential, the cell potential at under non-standard conditions. And so that brings me to these molarities. So these molarities are not in standard concentrations. So this reaction is not under standard conditions. So we got to use the Nernst equation to calculate the non-standard cell potential. So here we're going to use this. So here, so in order to use this, we need Q. Q is the reaction quotient. And so let me remind you that this expression of Q is based on the law of mass action, how concentrations are affecting whether or not a equilibrium is one way or the other, is more to the right or left. So here, Q, this is our equation here. We don't include solids or liquids in the expression. They don't have concentration. So liquids and solids, so this, and this is not going to be in the expression. So remember, it's going to be products over reactants minus the solids and liquids. So here we have Cu2 plus. So we're going to have the concentration of Cu2 plus. And then here we have a 3 coefficient, so that's going to be raised to the third power. So that's our products. So that's it for products. And then we have reactants. So we're going to ignore copper. And then we have aqueous manganese, permanganese ion, and H plus ion, our hydronium ion. So here we're going to have the concentration of MnO4 minus And we have a 2 coefficient there, so here we're going to have a square power. And then we're going to multiply by the concentration of H plus. So H plus. And here we have an 8, so that's going to be raised to the power of 8. So this is our expression for Q. And so now what we do is we take the molarities we're given. So here we have 2 molar for MnO4. We have 1 molar for the H plus, and we got 0.010 molar for the copper 2 plus ion. So then we plug all of that in. So this is going to be equal to, so copper, where's copper? 0.010. So that's going to be 0.010 cubed over, and MnO4, where's MnO4? 2. So we have 2.0. So that's going to be 2.0 raised to the power of 2. And then multiplied by hydrogen, 1.0 molar, so it's 1.0 to the power of 8. And so now we have our expression. Now we just calculate this, and when we calculate it, we get, what did I get for this? And we get 2.5 times 10 to the negative 7. So that's our Q. So now we have Q. So now we can plug that into our Nernst equation. So that means that let me write it over here. So I have E cell is equal to the standard cell potential, which we calculated here. So that's going to be 1.34 volts minus, and it's this 0.0592 minus 0.0592 volts over N. And again, N is the number of electrons that are being transferred in our reaction. So we have 6. So 6 electrons are being transferred. So 6 goes down there. That would be 6 moles of electrons. And then that's going to be the log of Q, which is 2.5. So 2.5 times 10, 2.5 times 10 to the negative 7. And so now all I need to do is calculate this out on my calculator. And when I do, I get 1.34 volts minus negative 0.065, negative 0.065 volts, 0.065, okay? And so therefore, finally, the cell potential under non-standard conditions is 1.41. So 1.41 volts. So that, ladies and gentlemen, is the cell potential under these non-standard conditions. So I hope this was helpful. If you enjoyed this video, then please, by all means, like the video, share it with your friends. Also hit that like button. And by the way, you should subscribe to my channel. Make sure you hit that notification bells. And when you do, click all, so that way you can be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.